I'd like to introduce Corina Pasareanu, who's an ex-colleague of mine from NASA Ames. Really cool work on test case generation, so I invited her to come over and tell us what they've been doing most recently.
Okay, thank you.
Sure.
So this is actually joint work with Willem Visser, who used to be at NASA Ames, but now he's at 7 Networks. And actually, he also gave a talk here, so maybe you will recognize some of the slides and ideas. Okay, so I will talk about combining symbolic execution and model checking for testing. And this is, as I said, the work with Willem Visser, but actually a lot of summer students also contributed to this work, so I listed them here. And also some other people from NASA Ames, David Bushnell, Peter Melitz, and Guillaume Brat. So the goal of this work is to detect errors in complex software. And by complex, I mean software that has data structures, arrays, concurrency, and so on. So I listed here several of the solutions to this problem of error detection, and this is a very simplified view. Actually, the borders between these different areas are blurred now. So one is software model checking, maybe with abstraction. For example, predicate abstraction is a popular research direction. So this is automatic, it's exhaustive, but of course it suffers from scalability issues. For example, explicit state model checking, and I will give a bit of background about this, so to see what I mean by this, cannot handle large, complex input domains. And because of the abstraction, the reported errors may be spurious. Another technique is static analysis. Again, this is automatic, it's scalable, it's exhaustive, but the reported errors may be spurious. So you might get a lot of warnings that don't correspond to real errors. And of course, yet another technique is simply testing. So the advantage is that reported errors are real, but of course, testing is not exhaustive, so it may miss important critical errors. But this is a well-accepted technique, and this is, for example, the technique accepted at NASA. And basically, we learn to sell our more advanced technique as testing techniques, because this is what people would accept. So our approach is to combine the strengths of exhaustive techniques, such as model checking and also symbolic execution, and I'll tell you what I mean by that, to enable testing. And basically, we combine them for test case generation. So this is like a very, very high-level introduction to model checking. So, and comparison with the more traditional simulation or testing. So the idea is that one models individual state machines for subsystems and features as maybe finite state machines. And then simulation and testing checks only some of the behaviors of the system. So of course, it may miss errors that were not analyzed. While model checking goes automatically through all the possible behaviors of the system. So it can handle millions of combinations in an automatic way. And usually model checking also gets a specification, for example, written in some temporal logic or some automata formalism that describes the expected behavior of the system. And the output is either that the property holds or that there is an error. And moreover, model checking also gives you an error trace that allows you to basically, it helps you to debug your system, to find the cause of the error. So in particular for our work, we use a model checker, which is called Java PathFinder. And this has been developed at NASA Ames since 1999, and actually John was part of the team that developed it, and it went through several phases. So this is an explicit state model checker for Java bytecode. And it is built on top of a custom-made Java virtual machine. So it is in some sense like an advanced virtual machine on which we can control the scheduling, we can control the state information, and we can perform abstractions and so on. And the focus of this model checker is on finding bugs. And they are concurrency related, such as deadlocks, data races, missed signals, and so on. Also Java runtime related, so for example, JPF looks for unhandled exceptions and so on. And it can also check for application-specific assertions, like Java assertions, and also it can check for safety properties implemented with some listener mechanism and so on. So JPF uses a variety of scalability enhancing mechanisms. And I listed some of them there, and then I put a bit of publicity for it, so it received some awards. And but the important point is that it is now open sourced, and so basically people can use it freely and also contribute to its development. So now, what do I mean by symbolic execution? So first of all, I'll say that we have extended JPF with a symbolic execution. And this is our enabling technology for test case generation. And I'll talk more about it. And we have several papers that are publicly available that describe this extension. And basically, for test case generation, we combine symbolic execution with model checking and constraint solving. And this extension applies both to executable models and to code. And it handles dynamic data structures as inputs, also arrays, loops, recursion, multithreading, and so on. And it generates an optimized test suite that satisfies coverage criteria as specified by the user. And it also reports coverage. And during test generation, because actually we use JPF as the underlying engine, it also checks for errors. So this is at a very high level what symbolic execution does. So basically, it's a systematic path exploration. And during path exploration, we generate and solve numeric constraints. And these constraints are gathered basically from the conditions in the code that is analyzed. So this is a little fragment of code, very simplified, from some code at NASA, actually, that we analyzed. So basically, there is a condition that checks if the pressure is less than some minimum value or greater than some maximum value. Then basically, do something, abort the mission, for example, because you are not in the parameters, otherwise continue, or something like that. So how would one test such a simple program? Of course, in a classical setting, you would just provide some inputs, for example, this value for pressure, and maybe the minimum and maximum values are defined in the code, and then you execute the code. And this will exercise only one branch of the if statement. Well, in contrast with symbolic execution, we do a non-standard execution that uses symbolic values rather than concrete values. So for example, for pressure, it will use some symbolic values, and maybe also for minimum and maximum. And during symbolic execution, it also maintains a path condition that is initially true. And it will be updated with the conditions that are analyzed in the code. So then for one path that corresponds to the first condition in the if branch, the path condition will be updated with this condition. Then the analysis engine, basically the model checker, will backtrack and explore another path corresponding to this condition. And then again, it will backtrack and it will explore yet another path. And then what we do, we get these path conditions we solve them, and we get the test input. So now we will obtain basically 3 sets of test inputs that will cover all the paths through the code. This is at a very high level what is going on here. And I listed here some applications of our techniques. So actually this summer we have been working on testing some NASA control software. And basically this was not a piece of software which was not very large, maybe 600 lines of code, but it had very complicated conditions. For example, the path conditions that were gathered by our analysis were up to 60 constraints or something like that. So manual testing is time consuming. For them it took 1 week and they could not obtain full coverage. We also performed some guided random testing, and again we could not obtain full coverage, but with our techniques we generated about 200 tests to obtain full coverage. And I'll talk a bit more about this example at the end of the talk. And the total execution time was less than 1 minute, and actually they used our test suite in regression testing to test an update to their code. And they found some major bug in the design of the code. So our test suite led to some serious redesign of their software. So I listed here another application. So the first one, in some sense, is some white box testing. We generate code from we generate tests from the analysis of the code, but we can also use our techniques in a black box fashion. For example, we applied these techniques for testing rover executive developed on NASA Ames. So this is a piece of software that receives plans which encode commands for a robot, and then it sends them to the hardware and also it monitors the execution of these plans and the environment, and it can abort the plan and so on. And basically for this application, we encoded the grammar for the language of this, for the planning language. And we also put some symbolic constraints on this grammar. And we were generating test plans with this technique to test the actual software. So this is a black box application. And again, all of these applications are documented in papers that we wrote. And we also have some test input generation techniques for Java classes, again in a black box and white box fashion. And I'll talk a bit more about this at the end of the talk. So this was basically a high-level overview of our tools and our applications. And now I will try to go a bit in more detail in describing more details about our techniques. So I will start with symbolic execution, which we did not invent. It was King who invented it in the 1970s. So basically, it enables analysis of programs with unspecified inputs. And as I already said, it executes a program on symbolic rather than concrete inputs. So hence, symbolic states represent sets of concrete states. And for each path, the analysis maintains a path condition that basically encodes the condition on the inputs for the execution to follow that particular path. And also, usually one during this analysis needs to check for the path condition satisfiability. And if it becomes infeasible, it means that the current path is no longer feasible, so the analysis should backtrack. And I did not put it here, but in essence, symbolic execution computes the pre- and post-condition of a piece of code. So one could also use this for some other analysis. We had a discussion at lunch about that. So a symbolic state now has symbolic values and expressions for variables, also a path condition and the traditional program counter, and also some thread scheduling information in case of multi-threaded programs. So this is a bit of a small example Again, I want to contrast standard concrete execution to symbolic execution. So on the left-hand side, we have some code that takes two inputs, x and y, and they are swapped if x is greater than y. So this is the code that swaps x and y. And here we check an assertion, and the idea is that this assertion should be unreachable because we did this swapping when x was greater than y. So if this was successful, this statement should be false. So again, with a concrete execution, we would start with some concrete values, for example, 1 and 0, and we would get a concrete execution trace. Now, in contrast with symbolic execution, the result is no longer a trace, but rather a tree. So this is basically the result of symbolically executing this piece of code. So initially, the path condition is true, and big X and big Y are the symbolic values for the inputs. Then the first if statement, the analysis considers both branches, and on one branch, the path condition is updated with this condition, and on the other one with the negation of it, corresponding to getting into this part of code. And again, here the path condition is updated. And notice that for the case corresponding to the assertion being reachable, the path condition becomes infeasible. So we use off-the-shelf decision procedures to check that. So basically, we will get that this assertion is unreachable. So now, traditionally, symbolic execution was defined for programs that take SCA. Yeah, sir. Yeah.
The condition is actually, but assert is not unreachable. Assert is reachable. Theoretically, this will never happen. However, you are declaring integers, and in case of overflow, you don't really know what's going to happen, right? So if both x and y are very close to the maximum value.
Yeah, so this is a simplified view. In reality, in your analysis, you can start with the path condition not true, but rather, for example, in order to model overflow, you would put some ranges. So then you would start with a known precondition. Or if you want, so you need to encode this extra logic to catch that. So this was just an idea, and there is a lot of work to encode that checks, but it's possible. So it's theoretically, and a lot of people are doing this. So this is a well-known technique. So now, as I said, the symbolic execution is worked traditionally for scalar data, and it usually has a problem with concurrency. And what we have done, among other people, was to generalize it to handle now, besides inputs or reals, besides integers or reals as inputs, also data structures. For example, how would we handle if, how would we analyze the method if the input is a list or a tree or a graph? Also, how would we handle arrays and so on? So our framework handles all these features here, and basically it handles concurrency and arbitrary control flow for free because JPF already handles that. So in particular for dynamically allocated data structures and arrays, we use a technique that we call lazy initialization, but this is akin to basically lazy evaluation. So we start the execution with uninitialized data, and we lazily initialize the heap as needed by our analysis. And I will give some examples. And again, I put here some papers that document this work. And as I said, Java PathFinder is used to generate and explore the symbolic execution tree. And we also handle aliasing in the input data explicitly. So basically, we enumerate all the possibilities in the input, and I will show an example. And we use off-the-shelf decision procedures to check for path conditions. And as I said, the model checker basically backtracks if the path condition becomes infeasible. And as you mentioned, of course, there is a lot of approximation happening and a lot of imprecision getting from the past conditions, and you can take different decisions. If you don't know enough information, you may choose to continue to explore the path, or maybe you may backtrack in case of testing, for example, where you want to be guaranteed that all the inputs exercise the code, and we can talk more about that offline. There are a lot of design decisions about what to do. And I'll also talk a bit about more advanced techniques that basically perform subsumption checking and abstraction for the symbolic states. So now let's look at another example that now has as input a list. So class node implements a singly linked list. LM is the element in a node of the list, and next points to the next element in the list. And swap node basically swaps the first two elements in the list if the first element is greater than the second one. This is the idea. And now let's assume we want to analyze swap nodes. So the implicit parameter to this method is the one pointed to by this. So this is what we do here, and these are the results of our analysis. So basically, we will output 7 configurations, and each configuration corresponds to one pass through the code. And because actually we don't have a loop here, because I'll talk a bit about that, so we have a complete analysis here. So for each input list, we also perform the output list. As I said, symbolic execution basically computes a summary of a method in terms of the inputs and the expected outputs, a symbolic summary of a method. And these summaries could be used for many other applications, not just for test case generation. And we've done some work on that, and other people also did. So here, question mark means that the element stored in this heap node is unconstrained, so it doesn't matter for this execution. And also this yellow blob means that, again, the next field of the second element is unconstrained. So the analysis did not reach that point. It could be null, it could be a new node, another node. It doesn't matter for this analysis. And now I also want to tell you that, for example, we also check properties during this generation. So assume we did not have this check that next is not null. And then our analysis, of course, will discover this null pointer exception. So now I will illustrate, I will just give a bit of more intuition about this lazy initialization. So let's assume we want to execute this next equals t.next. And this is the current heap configuration. So we have a list with 2 elements. T points to the second element. And the next field of E1 is unconstrained, undefined. So what our analysis will do, it will first try to initialize this blob to all the possible values according to all the aliasing possibilities in the input. And then it will apply the standard Java execution. So this is the idea here. So for example, here we will have 4 possible configurations, one corresponding to null, another one to a new node with unconstrained elements, and then also for 2 configurations corresponding to some circularity in the input list. And then, as I said, it will apply the normal Java semantics. So now, because next is initialized, it can do next equals t.next, because t.next is defined. And again, I'm doing a bit of hand waving here, because for test input generation, we also need to maintain some mappings, because you have destructive updates, so you need to reconstruct the input lists in order to present them to the user to reproduce this information, but we can discuss a bit more about this offline. And another feature of our analysis is that we can handle preconditions. So instead of starting the analysis with a true precondition, meaning the inputs are unconstrained, one can, for example, specify as a precondition that the input list is acyclic, and then these two configurations would not be possible. So our analysis will check that, and it will not consider the paths following these configurations. Again, this is a bit more complicated because when you have this, we call them complex preconditions that go iteratively through a data structure. Things are not that simple, so we do some approximation, and in some cases, our analysis will continue from here. So we can talk a bit more about this again offline. So this is the result of applying basically next equals t.next. So now I'll talk a bit about the implementation. So our initial implementation was first done by instrumentation, basically by a source-to-source transformation. And the idea was that we replaced the concrete types with symbolic types and concrete operations with symbolic operations. For example, instead of integers, we would have class that handles symbolic integers, and then we would replace plus, minus, all the operations with method calls that implement these operations. And again, for field operations, we would replace set and get next, for example, with this lazy initialization algorithm. And then the advantage of this is the generality. In principle, one can apply then any model checker to perform this analysis, or one could simply run Java and get basically symbolic execution along one run. So we also, I'll talk a bit about the decision procedures that we used. So we started with the Omega library for integer linear constraints. And then we have one of our students, Saswat Anand, developed a common an interface, a general interface to several decision procedures. And we have interface with some other decision procedures. And our idea is to basically plug in whatever different decision procedures and solvers to our analysis, or the user could customize them depending on the application domain. Now I'll talk a bit about state matching. So actually, performing symbolic execution on looping programs may result in an infinite execution tree. So what one can do is, especially since our goal here is testing, is to perform a search with limited depth, or to put a limit on the number of constraints along one path, or maybe to simply limit, for example, the heap nodes in the inputs or things like that. But we have also investigated a bit more advanced techniques that basically perform subsumption checking. So the idea is now, as I said, a symbolic state now represents a set of possibly infinite set of concrete states. So then you need to check some logical implication between these symbolic states in order to perform this analysis. And the idea is that once you so during model checking, you would store these symbolic states, and then when you generate a new symbolic state and you see that it was subsumed by an already stored symbolic state, the model checker can safely backtrack, because it means that the previous run already covered for the successors of this run. So this is how one would use state matching or symbolic subsumption in this case during model checking. And yeah, so I'm not sure if I should go into a lot of detail here, but basically what we do, we normalize the heap. So basically, the state of a Java program contains all the heap information. We normalize it with a depth-first search traversal. And then we obtain some unique labeling for some matched nodes, and we check logical implication between numeric constraints. And I can give an example just to give an idea, but again, we will need to talk in more detail about this. So let's assume that this is the stored state, and then the model checker maybe went on a different path and generated a new state. And as I said, the goal is to see if this new state is somehow covered by the old state, because then it means that it can safely be discarded in our search. And what we do here is, as I said, we first do this depth first search traversal, and we try to match the nodes in these two graphs. And this yellow blob, basically, as I said, it means that the heap is unconstrained at that point. So, of course, it can be initialized to this subgraph. So this is, let's say, the intuition why these two structures match. And also, we do some normalization of the data stored into the heap to also check a logical implication into the data that is stored into the heap. So now the problem is that even with subsumption checking, this is not enough to ensure termination, because we might still have an infinite number of symbolic states. So one needs to also do some form of abstraction to further limit the search space. And we have implemented some automated support in Java PathFinder for this. Basically, the idea is to store now abstract versions of the explored symbolic states. So basically, they are like compact encodings of the symbolic states that maybe lose some information, but hopefully they are enough to maybe obtain good coverage of the code. And then we use subsumption checking to determine if an abstract state is revisited. And again, based on this, we decide if the search should continue or backtrack. So this analysis is no longer complete. It explores an under-approximation of the real program behavior. So now we are more in the testing domain. We might miss some errors, but so the state space that is explored in some sense depends on the quality of the abstractions that we use. But as I said, this still preserves errors to the properties that we are interested in, and it's useful for testing. And we have automated support for two abstractions. One is for singly linked lists, and another one for arrays. And they are called shape abstractions. They are actually inspired by the work on shape analysis. There is a tool, TVLA, for example, at Wisconsin, that performs shape analysis. So the idea is to preserve some information about the heap, the shape of the heap, and maybe throw away some other information that maybe the values of local variables, or to summarize some. This is the high-level idea. I'll give an example. So in these particular abstractions for lists, the idea is to summarize contiguous list elements that are not pointed to by program variables into so-called summary nodes. And also the data, the numeric values that are stored in these nodes are also summarized. So basically now a summary node will encode the union of the values of the nodes that were summarized. And then we apply subsumption checking to these abstracted heap structures that have these summarized nodes. And we also defined an abstraction for arrays that uses these singly linked lists. And actually people in the shape analysis area, so this is an active area of research, and there are a lot of abstractions defined for more general graphs that have some constraints. And our idea is to borrow those abstractions into our analysis. What they do usually is an over-approximating analysis. So they try to cover all the possible paths, and maybe too many because of this. But we use them in this non-standard way. So this is just an example of the usefulness of this abstraction. So let's assume we had on the left-hand side a symbolic state. So again, it has it is represented by some heap configuration with some unconstrained data, and also some constraints on the values stored in the list. And then let's say that the model checker explored, generated another configuration, maybe on another path. And actually our initial subsumption checking algorithm will find that these two structures cannot be matched, basically because here we have one node between so we distinguish between the first node pointed to by this and the third node pointed to by a local variable n, for example. While here we have two nodes that are in between these kind of nodes. But with shape abstractions, we can actually say, okay, we don't care how many nodes are between this and the one pointed to by n. So we put them together here, and suddenly our subsumption checking algorithm will match them. So at this point, the model checker will be instructed to backtrack, not to consider successors of this state. Well, this is very technical, but let's see some results for these techniques. So I'll talk a bit about some applications of this JPF-SC, JPF symbolic execution extension. So we have some experiments reported in some ISTA papers that basically apply these techniques in a black box fashion. So the idea is to encode the so-called class invariant as a Java predicate, and then to apply our techniques from that Java predicate. And the result will be to generate different structures that satisfy the class invariant. Also, we applied them in a white box fashion. So now we run symbolic execution directly on the Java methods and use the class invariant as preconditions. And we compare these methods in this paper. And we also performed work on test sequence generation, and I'll talk a bit more about this later. Now, as I said, actually, symbolic execution is a general technique that can be used also in proving program correctness. We have played a bit with generation of loop invariants for it. And actually, again, at lunchtime, we were discussing about this technique. So in some sense, symbolic execution gives you for free specifications to check. So you can apply it, and you would get the preconditions and postconditions, and then just stick them in the methods that you want to check as assertions, and now you have a contract for your class, and this could help later with testing or regression testing and things like that. So this could be another interesting application. And also we apply them to error detection in concurrent software, and also in test input generation for some flight control software that I talked at the beginning. So this is a bit of information about test sequence generation for Java containers. So we analyzed 4 containers, meaning namely binary tree, Fibonacci heap, binomial heap, and tree map. And now all of these, our results are available with the JPF distribution. And actually now a lot of people use these examples as a benchmark for their testing techniques. So what we aimed here was to explore method call sequences with the help of Java PathFinder, and to match states between calls to avoid generation of redundant states. Tests. Okay, sorry, it's a mistake. And also we experimented with performing abstract matching on the shape of the containers. So here we did a simpler abstraction than the one that I described, where basically we just compared the shapes of these containers between method calls, and we threw away the numeric data encoded into these containers. So basically the output of a technique is a sequence of this form. So first you would create the binary tree, and then you would add 2 values and maybe remove 1. So this is a test case now for us. And we just checked for the default properties that JPF checks, like no runtime exceptions thrown. So we performed a comparison between explicit state model checking, also with some symmetry reduction, meaning with some reductions that are encoded in JPF to take advantage of the symmetry in the heap of the program that is analyzed. We also applied symbolic execution with subsumption checking, and also symbolic and concrete execution with abstract matching. And we also compared everything with random testing. And for coverage, we compared these techniques in terms of statement coverage. So basically, we measured how many statements are covered in the code. But also, we considered a more sophisticated coverage, namely predicate coverage, which was introduced by Tom Ball from Microsoft. So the idea there is to get some predicates from the conditions in the code and try to cover all the possible combinations of those predicates. So this, in some sense, mimics a bit. It's harder to achieve. It tries to stress the techniques to cover more of the state space of the programs being analyzed. So our results were that symbolic execution worked better than explicit model checking, and actually that model checking with shape abstraction gave the best results. So we infer that at least for containers, just maintaining the shape of them is good enough to obtain very good coverage. And this is not surprising because obviously the shape of a binary tree would give a good indication of the data that is stored in the binary tree. And also, it was interesting that actually random testing gave pretty good results, but it requires longer sequences to achieve good coverage. And now there is actually a debate if longer sequences are better than shorter sequences. And yeah, we need to investigate more which one is good for testing. So I'll go back a bit to that example that I talked at the beginning that was for test input generation for NASA software. So this was an example which I said, although it was not very large, it had very complicated conditions. So random testing performed very poorly there. So in some sense, it was the ideal application for symbolic execution that tries to go systematically through all the conditions. And so basically, we checked this abort logic that has a lot of conditions that encode the so-called flight rules. And if these flight rules are violated, the logic is supposed to issue an abort. And basically, we generated, as I said, 200 test cases. What was interesting is that we were also able to customize the coverage that they want. So, for example, our collaborators, the developers of this code, were interested in covering all flight rules and board combinations. And the point is that one can customize what kind of coverage wants to do and pretty easily with a listener mechanism in JPF. And another point that I wanted to make is that we want to work on integrating this symbolic execution-based test generation, which is in essence a unit-level testing technique with end-to-end simulation. And so the problem with applying this technique at the unit level is that often the input data is constrained by some information from the environment, from the rest of the system. For example, for this code from NASA, for the abort logic, we generated a test case where the inertial velocity was 240,000 feet per second, and the altitude was 0. And our collaborator joked, and he said it must have been a really bad day because it's impossible to have this. So physically, it's impossible. And actually, in the whole, we just analyzed a very small portion of the whole system that encodes physical models that would have these constraints. So what we want to do is actually to perform some end-to-end system-level simulations and to learn these constraints and then to put them as preconditions into our analysis. And we have a collaboration and we are working on that. And actually, we have some initial results. So basically, we were able to eliminate test cases that were impossible to these physical laws with this analysis. Okay, so I've just listed here quickly some related approaches. So one is a Cora tool developed at MIT, and actually Safras Khurshid was a summer student, and we started with him this project in 2003. But Cora is applied as for black box test generation. So basically what we did in some sense is a generalization of that tool. Then there is another popular trend which performs so-called concolic execution. So the idea is that you run a program on some concrete inputs, and during that concrete execution, you would also gather the symbolic constraints. So basically, you do a symbolic execution analysis along one path. And then you take the constraints, you negate one conjunct in the constraints, solve them, and then you get inputs that will steer the execution towards another path that will exercise different parts of the code, and so on. And this was started by Patrice Godefroy, who is now at Microsoft, and also Kushik Sen, who is at Berkeley now. And there are several different approaches that do that. Several different tools for C and Java that perform that. We also had another approach that is similar to what I presented here, that basically performs concrete model checking with a different form of symbolic analysis, which is called predicate abstraction and refinement, but I will not go into details with that. There is another tool which is called Simstra, that again performs some symbolic execution with subsumption checking between method calls. Then Dawson Engler at Stanford also basically works on this kind of concolic execution. And I listed more approaches here. So now as current and future work, this summer we have worked on a new symbolic execution framework which no longer uses code instrumentation. So basically it was moved inside JPF, and it works by a non-standard interpretation of bytecode. So we have an extension that performs, for each bytecode, performs this symbolic analysis that we discussed. And actually the symbolic information is propagated via attributes associated with program variables, the operands on the stack, and so on. And this is quite nice because actually with those attributes you can encode other analyses. Now you can propagate whatever information you want. And actually this is also used for checking, for example, runtime errors and things like that. And now we use another decision procedure that I found on SourceForge. And it's called Choco. And the advantage of it is that it's pure Java. So it's a good... it's good for development because now many people work on this framework, so it's easy to, it works on any platform, so this is what we use. And later we want to integrate the other decision procedures for it. And Choco actually handles both linear and non-linear constraints, and also integer and real constraints. But of course it might time out, it has the inherent limitations, decidability limitation. And everything is available from Java PathFinder. And now basically it's a push button technology. And as I said, one can use these techniques, symbolic execution, not only for testing, but also for other analysis. So this is another characteristic of our this new framework is that, for example, symbolic execution can be started from any point in the program. So basically you could simply execute your program and have all the concrete information, and at some point decide to do it symbolically. And this has the advantage that you may still use some concrete values from the context, because you may pick which values to become symbolic. So let's say for a method, you would decide to use symbolic parameters, but all the global information will be concrete. So this would give precise information about the context. And as I said, we are working on integration with system-level simulation, where we want to basically perform Monte Carlo simulations to obtain ranges and actually constraints for the inputs. Also, we have Peter, one of my colleagues at Ames, has a recent extension, JPF extension, that models UML state charts. And of course, our techniques apply for free there. And we are also working now on using symbolic execution to help regression testing. So the idea would be that you tested your code, and now some parts were changed. So we want to identify which code was changed, and then generate tests only that exercise that change. And of course, one could apply symbolic execution for that. And to do more applications. Okay, so thank you. This was my talk. So, do you have questions? I hope I did not confuse people.
Well, I had a question. So when you do the test sequence generation, I didn't completely understand what the state was.
Yeah, I went very quickly. Yeah, so basically there we did something very simple. We created a driver for Java PathFinder that basically non-deterministically, for example, in this case, we'll call add and remove. And then after each method call, we would try to match the state of the container. So we would have an abstraction that basically we would not do state matching inside the method, but just outside. So after an add, you would have a new state for the tree that will have one element. After another add, we'll have a tree with two elements, but after a remove, you'll go back to one element, which you already explored on a previous path. So this was the idea. Yeah, yeah. And then with this state matching, as I said, in some sense, the values that are added were not that important. So it was enough just to match on the shape of the tree.
The abstraction on the shape, so the abstract shape matching where you showed you merged like intermediate nodes that weren't pointed to by program variables. So that didn't apply.
No, so here actually we did not even summarize. We just threw away the numbers and that's it. And it was good enough. So a very rough abstraction actually performed the best out of all the techniques. So some of them were very complicated. For example, tree map. I don't have the results. I didn't have time to put them, and now I forgot exactly. Just that it was challenging to obtain good coverage for these containers.
Okay, so you were looking for coverage of the code in all of the methods that you called, like add and remove and all the different cases.
And they call a lot of these were the public method, but they call a lot of other methods. Yeah, so this is the idea, to try to cover add and remove. A pretty simple problem actually, but it's difficult in practice. So.
I'm wondering about some of the runtime characteristics of the tool. How scalable is it? So how?
It's a good question. We are first putting it into place, but as I said, it's a unit. It's a unit level analysis tool. At least this is what I believe, and I think with these features that basically you can run your tool in. We can also turn on and off the state matching, so you can maybe just launch the tool and go deep into the state space and then do this detailed analysis. We think we might get interesting results, but of course scalability is a problem. So that's why we also want to combine it with these Monte Carlo simulations to have precise unit level analysis. This is what I would like, how I would see it useful.
So I'm curious, kind of connecting onto this. Obviously, the 600-line code example you said was small, but what's the largest code base that you have analyzed this? And the second question is, did you use the tool to analyze the implementation of the tool?
No, this is a classical question, but we didn't, because as I said, this is good for unit testing. I think. So if you have complicated code, but at the unit level, so it's not, if you have millions of lines of code, then you should choose to focus on something that bothers you or not apply to the whole. So in some sense, I could claim, okay, we can launch, Peter applied JPF to, I forgot which big application that had millions of lines of code. But then what I could do with this analysis would be to focus it on some portion inside it that maybe is problematic. For example, for this small portion that is again a part of a big simulation environment for them, we were able to generate very interesting test cases that led to some redesign even of other parts of the code. But yeah. And yeah, we didn't apply it to JPF itself. I think William actually applied some static analysis to JPF. But this is, yeah, a different level. It is very detailed, so it wouldn't scale to millions of lines of code. Although, again, we want to, so first of all, we want to put this in place. We are working on integrating Choco for reals, it calls it, but you can set the precision, and you have to play with a lot of parameters, also with the timeout. Sometimes the decision procedure doesn't come back, and we would like to allow the user to customize that. And then one can, for example, there are approaches that try to scale this with some compositional analysis. So you would apply, let's say, symbolic execution to a method or a procedure, compute the summary, meaning the inputs and the outputs, the input-output mapping. And then when you analyze the program that calls that procedure, you would just plug in the summary or things like that. So one could do that, but we didn't yet. So there is still a lot of work. But what works now is at the unit level. Actually, it works well.
So when you did this is thinking about scalability. So when you did the test sequence generation, you're matching the state of basically the example container that you're trying to test. So you have this, whatever, a tree, and you're trying to, add things to it and generate all these different trees. Yeah. And then you're matching on, your state matching is on the shape of the tree that comes back after each operation. So is that your entire state space then that you're storing? Is just,
yeah, but it's very expensive. For example, for sequences of, I forgot now, I don't have the slides, but for sequences longer than 17 or something that were needed to achieve some deep coverage, all the tools would chuckle. And chuckle, is this the good? Choke. And random testing could not cover. So you need to go this extra step if you really want that coverage. Okay, if you don't care, it's fine. And
was it like the size of the things that you
yeah, it's very complicated.
To the constraint solver? I mean,
no, not the constraint solver. No. Just the sheer complexity. If you have, for example, for tree map, and you have a history of 17 methods, that was complicated. It was already very complicated for the model checker.
But complicated in terms of like the size of the state.
Yeah, it will run out of memory.
Okay.
And actually all the techniques, so now a lot of people, it's an active area of research, and they use this as a benchmark and you'll see it's very difficult to obtain good coverage. Maybe it doesn't matter.
You're still storing the concrete states of the execution.
Yeah, you don't. And
Even
you
though
still,
you're only
I don't have the reason.
Abstractly at certain points in the program, you're still storing the.
Yeah, I think I forgot now, but it depends. So if you do the abstraction, maybe we went to 20. So for some, I don't have the data now, and I forgot now a bit. But for some coverage, this predicate coverage that we defined, you needed longer sequences that you could obtain only with this abstract matching. So this was the best indeed that you could do. But yeah. But yeah, of course it's also an implementation issue. The truth is that, for example, now other people build after us, so we still use a general purpose model checker, and for us it's a good research tool, but other people build dedicated tools, for example, just to generate test sequences, and they are of course better in terms of they run faster. They just don't maintain all the information like JPF does, but just, let's say, maintain some good encoding of the abstract state between method calls. For example, Simstra does something like that, the tool of Tao. So if you would have a dedicated tool, then it could be improved, obviously. But for us, this is a vehicle to experiment with different techniques. So, okay.
Thank you.
Okay.